is there?
Yeah. So again, I don't believe in too much formality, So
Exactly.
we have been working with Tari, Deep Kappa for a long time, and we are thrilled to have them here. And I think this is the third presentation, So and we are recording as well, so that way anytime later if you want to refer, you can refer as well. You can go back to meetup page. That's where the recording link will be posting. Okay, thanks to for everybody for joining. Tari, you can start. Thank you.
Thank you very much, Professor Veerasamy. Once again, this is the third presentation, as Professor Veerasamy just mentioned. The other two presentations we did was, the first one was how to create an AI startup. And Fred, who is here with me, a good colleague and is CEO and founder of the company in Houston, in Texas, out there in US, close to you in Dallas, is the one. He gave a presentation on all the challenges you actually run into when you're actually conceptualizing and incubating an idea, and taking an idea from incubation all the way to bringing it to a great application that customers will use on a daily basis and efficiently and operationalize their mundane tasks through these tools. It's a huge journey. It's an exciting journey. So that was the first presentation. The second presentation was about how to actually create effective, efficient pipelines as if you were on Amazon or on Netflix or any other company, to automate tasks as much as possible. So each time you are having new features, think in terms of TikTok or any of the apps you use on a daily basis. When you have some new feature that you can do this, have a filter, do create some kind of all these lovely emojis. These are all features you need to add into commercial applications as well. And if you have automated pipelines, things become a lot easier. In this talk today, what we are going to be talking about is taking a step all the way back into the laboratory. So when you're doing an AI startup, and if you are genuinely an AI startup, meaning really your hands and feet dug in dirty and deep into machine learning and computer vision sort of models, you will learn to understand what is it that actually what is the problem I'm trying to solve through the lens of a data science or a researcher. So in this talk, before we get into introducing my colleagues, let me just give you a bit of a perspective of artificial intelligence. And this is just, think it's, in terms of, for those who are not familiar with these terms, I'm just kicking it off because the next 30, 40 minutes will be interesting. They will also be a little bit intensive in terms of, the quantity of information that will travel in this conversation. So basically, just want to sketch here. So machine learning has been used in the industry for a long time. So basically what you're seeing here is people have been doing machine learning for the past few decades. And I'm just giving you a simple example of, let's say if you had a car and you needed to do some form of detection, if it's a car or if it's a truck or some other mode of transportation. In the days before deep learning, people would do feature extraction, take interesting features like it has 4 wheels, it has a flashlight or headlights, stuff like that, the shapes of a vehicle, and you do feature extraction. Essentially, then you throw it into a model. We call it a model, an artificial intelligence model, a machine learning model, and you do simple classification based on the features. And then the output is either it's a car or it's not a car. Now, with the advent of deep learning, and when I say deep learning, you will hear this term used by my colleagues here often. It is a field that has been inspired by the world of neuroscience. So essentially, you're trying to make the computer see and think like a human or a mammal, actually. And what you try to do is, if you're a human, you're not sitting around doing feature extraction. You look at a car, you know it's a car. You look at a dog, you know it's a dog. You look at an apple, you know it's an apple. You look at an unidentified object, you categorize that as something unidentified. So you don't do all this stuff. So in deep learning, the biggest actually sort of change that happened from machine learning transitioning to deep learning is that it automatically does feature extraction. Obviously, there are algorithms, intelligent algorithms, and architectures like convolution neural network. They're used in order to do that. So basically, you're just automating everything, and that's why you can instantaneously see if it's a car, it's not a car, or maybe it's something else. It's a truck. You can have more classes actually added to it. So this is basically a bit of a high level sort of perspective. I just want to give you so you get a bit of an idea before you start going a bit deeper into understanding how did these guys spend time inventing. So we invented some new stuff that we have presented into worldwide conferences in the across Canada, Middle East, and my colleagues will be talking about it. Again, so that is this part of the story. And when you say artificial intelligence, basically you're trying to do at least, no one has reached that level of general intelligence. What you're trying to do is you're trying to throw a certain environment inside a mathematical function to understand, let's say in this case, I just put world in it, but you're basically trying to understand the environment around yourself. So like I said, machine learning, you had a certain task, you did feature extraction, and there was a human in the loop. In deep learning, essentially, it's all based on learning. So it's about learning, constantly learning, and the more data you have, the better a system can learn. That's that sort of big difference between machine learning and deep learning. In machine learning, you can have 10,000 rows in a table, and you can do some simple sort of regression techniques. In deep learning, you would be better off if you used, if you had large, vast quantities of data, and through that, you can simulate, imitate, mimic learning as if the machine was a mammal or a human being. So that's something I just wanted to kind of give you guys a bit of a perspective. So basically, that's the part that is automated. And I showed this presentation last week as well. So this is the whole sort of ecosystem we call machine learning operations. So the ML ops lifecycle involves, last week we spoke about this part, the center, and today we're going to be talking about this part. Actually, this is what all the stuff my colleagues will be talking about on the left. So this is what we're going to be talking about. If you want to get a bit of a detailed understanding of what the machine learning operations is, or ML ops is, please refer to the previous workshop we gave a week ago, or actually last Monday. And I've spoken in greater detail about that. How do you actually take an idea, convert it into data, and then create data sets, and then essentially train model, take the best model, and start giving it to the guys in the production so they can start exposing these models in form of APIs to create wonderful and breathtaking apps. We will revisit these concepts again. So having said that, let me introduce my colleagues. Two of our wonderful colleagues, Kwame and Javed, they both are PhD candidates doing geophysics in IIT Kharagpur, one of the top institutes in India, a wonderful institute where we have a lot of folks, alumni working with us. And these two gentlemen will take you into a journey of actually two things. So invention, the biggest part is, how did we invent all these things? How did it actually come from ideas, and how did we actually create architectures and models out of this? So this is a sort of genuine invention. No one has invented this. Yeah. And we are constantly improving upon it. The second part will be of innovation. So we take invention and how do we start placing these great and wonderful ideas that have been quantified in from theorems from to algorithms and eventually into software. So how do we take this and what kind of challenges we ran into? So innovation and then invention and then innovation. So those are the two concepts these two wonderful gentlemen will be talking about. So with that, I'll put myself on mute. Kwame, you can take away. You can present your slide. And I'll be here at the back end trying to help manage and help you guys with managing your time as well.
Hi guys, thank you Terry for explaining all these. So let me share my screen. Can you stop sharing your screen?
I have stopped sharing.
Okay, thank you.
I think, yes, I did.
I hope you can see my screen.
Yeah.
Yeah, okay. So I'm Kamal Naseem. I'm from India. I've been working with Deepka for a year. Actually, I am actually AI instructor at Live AI. I'm also a AI researcher and have been working in a research department at Deep Kappa. As already told by Terry, that I'm a PhD candidate at IIT Kharagpur in India. Okay. So here, as Terry already mentioned, that we will be talking. This talk will be divided into two segments, that is invention and then further into innovations. So here, I'll be discussing about what the invention we did at our own DK labs. So as Terry earlier said that earlier it used to be machine learning, and then after that, I mean, when computation capabilities increased, we introduced we came to we started working on deep learning, and then there are actually several sub classifications in deep learning, such as natural language processing, computer vision. So this particular invention relates with computer vision, which you must have already heard what computer vision is. So basically, in computer vision, there are two types of problem. One is classification, and another one is segmentation. So in a classification problem, usually you would see that given an image, it will have a single particular label, that whether or not this particular image is of dog, or is it a cat, or is it some unknown object. So that is what classification problem is. While in segmentation problem, you don't have instead of having single label, you have to predict labels at each pixel. So as you can see that, I mean, you will have, there are actually, this is a basically uh, a binary segmentation, where you have to identify where the dog is present, while you will have to annotate it with black, with all the background images. So similarly, in our geophysics, there is a problem where you try to basically, this is the raw seismic image. What raw seismic image is, it's basically a image of inside of the earth. We call it subsurface. Basically, it's an image of inside of the earth, where, I mean, we can and it is acquired by sending sound waves inside the earth, and then it gets reflected. It's basically, there is a, I mean, huge process in order to acquire this data. And once we have acquired this data, this is how that data looks like. And then we have to figure out the layers. As you can see from this image, that there are actually layerings inside the earth. This is the layer, this is the layer, these are the layers. So we have to basically try to figure out where, what are those layers in this problem statement. Why is it necessary? Because it is actually very first step in towards hydrocarbon exploration. Before we go towards finding out where probable hydrocarbon zones are present inside the earth, we first have to find out what are the layers, and then based on the study area, based on the geology, we will have to figure out which particular zone will have hydrocarbon zones, which particular zones will not have hydrocarbon zones. So based on that, so that is why this study is actually very important. So we have to figure out where the all the layers. So this is basically the ground truth in our case, and this is the input to our model. This will be the input to our model. In a geological term, we called it facies, but I mean, in a day-to-day term, it's just layers within the earth surface. So this is the architecture which we have used. As Terry was earlier mentioned, that we have used computer vision, a computer vision algorithm, and this is how a typical computer vision segmentation problem looks network looks like. This is basically an encoder. So segmentation network consists of two parts. One is encoder and another one is decoder. Encoder tries to capture as much information from the given image. The given image is basically this, basically a cropped part of this image. So encoder tries to capture as many information from this image, from this input image, and then decoder tries to decode it again in order to regain the same size, but with obviously with the ground truths. So we have used actually this the basis of this model was a model named UNIT, which was actually came from a biomedical application. So we have modified that original unit with residual blocks. What residual blocks does is that it adds a skip connection to the network. Earlier, in the vanilla unit, there was no skip connection. We introduced this skip connection into this into the original unit connection, into the original unit network. And then there is another this block is basically a ASPP module. What ASPP module is, it's basically Atlas Spatial Pyramid Pooling. What basically it does, it tries to capture a multi-scale level features. It tries to look I mean, basically you can say that if you will look at a model tries to look at a different scale. And it was developed by Google in a paper named Deep Lab V3. So what we try to do, so first we made an improvement by introducing this residual block and transpose residual block, and on top of that we introduced this ASPP module, Atlas Special Pyramid Pooling, in the original unit by replacing it with this convolutional layers. So this is how we actually invented this architecture. And this is the result that we have received. So as I already showed you that this was the seismic section which will be the input to the model, and then our aim is to predict this seismic facies, basically the layers within the earth's surface. And this was the prediction that we got. Now the
Mhm.
prediction and the original faces match to some extent, while there are some misclassification presence. Now we obviously are continuously developing and doing research work, so there is a room for improvement in this model. But yeah, so this is what we have received, and as you can see that here are also some misclassification present over here. But overall, as you can see that it our model has done a pretty good decent job, and actually it has achieved a state of the art result. Yeah. Okay, so another section is that it is a domain adaptation network. So there is a computer vision problem, and then inside the computer vision problem, there is this classification and segmentation problem. After that, there is something called transfer learning. What transfer learning does is basically you train your model on something on some other data, and then if you don't have enough data and then you have a data which doesn't have enough labels, so what you will do is you will get the already trained model and do a fine tuning to the already existing model. And this domain adaptation methodology is sub part of this transfer learning. So what this domain adaptation does is, in a classical machine learning approach, there is a big assumption that training data, test data, and validation data, all these should have similar distribution. This is basically a big catch in classical machine learning approach. But as you know that this is basically a scan of cardiac heart. But visually, with to our eyes, though we can recognize that both the scans are of heart, but but these are actually different. The data distribution varies, as you can see over here. But so our eyes can learn this, but a machine learning model is going to get confused that whether or not this is a heart image or a heart scan, or is it something else. Similarly, if we try to train our model on MS Coco dataset, which basically most of the time has a has a bus has basically cars or buses of white colors, and if we try to give our give if we try to predict using this image, then it's very obvious that our model's performance is going to decrease drastically. So in order to fill this gap, this domain adaptation network was actually introduced. And so in the context of geophysics, what happens is that though the reflection pattern, as you can see, is same, but as you move from one place to another and do the survey, reflection pattern remains same, but the data distribution varies, as you can see over here. So to our eyes, it seems normal, but a machine is unable to understand this thing. So in order to understand this thing, this domain adaptation network was introduced. So what the source domain and target domain is, source domain is the one which will have actually enough labels, ground truths, but target domain is not going to have enough labels. So yeah, so this
Mm-hmm.
is the network which we have used. uh, Let me show you this network. So this network that you can see, this particular network is actually taken from this network. It's basically the encoder part of our already previous invention that we did. So we took that encoder part, and then since this is a classification problem as opposed to segmentation problem, which I discussed a few minutes ago, we introduced fully connected layers to the model, and you can see that there will be two parallel networks, one for source domain and another for target domains. And as already told, that source domain is going to have enough, source domain will going to have enough training data, while the target domain will not have enough training data, or have zero ground truths or labels. So in that case, the source domain will have one network, and target domain will have another network, but both the networks will have shared weights, or basically what you can say is parameters. Both will have same parameters, shared parameters. And we will apply the classification loss. Basically, classification loss is that, is it matching with the ground truth, whatever this network has predicted, is it matching with the ground truth? If not, then we will have to find that loss, that what is the loss actually. So this is the loss which we will be finding, and this is basically the choral loss, or choral loss that we have applied in this domain adaptation methodology. We can apply choral loss at many layers, and we have applied this choral loss at three different layers. Now I'll be talking about what this choral loss actually is. So basically what we try to do is we try to find the covariance matrix of source domain and target domain, and then we try to take a Frobenius norm. And after taking the Frobenius norm, that is what we get, the choral loss. And we apply this choral loss at each layer. Now before we try to optimize our weights or parameters of the model, we add up both classification loss, this classification loss, as well as these three choral loss. And then once we have added this choral loss, then we try to optimize our model weights based on this loss.
Mm.
And this is the result that we have received. This direct learning is basically that give direct learning is basically we have trained our model on source data, but we are trying to predict our target data, but we are trying to use that model which was trained on source data to predict on the target data. Now, as I obviously said, that if the data distribution will change, our model performance is going to decrease drastically. A classical machine learning approach will decrease drastically, will give poor results. Now, as it is very obvious from this result that, I mean, the results are actually very poor. But when we introduced this domain adaptation methodology, this EarthAdaptNet, we were able to see a huge plunge in the accuracy of all the classes. As you can see that there is a 13% accuracy increase in class 1, while around 40% increase in class 2, also around 60% accuracy increase in class 3. So this is how we actually introduce this domain adaptation methodology, and this is how it actually helped. So now, even though, so now how this methodology is going to help in industry. So suppose that you go to a new place and you don't have any new data, any labels present there. So what you will do is, now that you already have a source domain data, so you will take that data and then try to train your domain adaptation methodology and try to predict on the target data. So that's how it's going to help. Now I'll pass
Mm-hmm.
on to Javed, that he will
Just I wanted
discuss.
to add one thing. I If you could just go 2 slides back, Palmer. Here, one more. Yeah. So you heard sometimes it's kind of seems and feels like mumbo jumbo. No, the slide ahead. Yeah, this one.
Is this?
So you heard Kwame talk about a Frobenius norm. Frobenius norm actually is, and I come to Dallas quite often. I know, unfortunately, because of COVID, we are not able to do this in the last year and a half. And we go into deeper details of really teaching you how sort of matrix multiplication works. So basically, a Frobenius norm is, it's also called Euclidean norm. And sometimes people also miss sort of represent it by calling it a vector norm. So basically, it's a very simple sort of a matrix multiplication that is a square root of the sum of absolute squares of the elements. That's what it is. So it's no, all these terms sometimes, back in at university myself, when you're starting up with these ideas, you have to sort of, go back into your matrices, basic understanding of calculus and matrices. So don't worry too much about these terms. These are very simple terms. Essentially, it's all about doing matrix multiplication. That is what sort of, in machine learning models, things have become super exciting. And matrix multiplication become a lot more exciting when you start throwing these calculations inside, GPUs, and things become super fun. So this is what we've been doing, and training these models with the GPUs, where Javed is going to talk about when he starts talking about the real world. How did we take this invention into innovation? He's going to talk about that in detail and how difficult this task was, and then eventually how did we put these multiplications, matrix multiplications, into GPUs. So just wanted to give you that. So don't sort of, start getting nervous if you start hearing terms. That's part of learning, which is such a fascinating field, what AI is becoming. So go ahead. Just wanted to add that
Yeah.
in the middle.
So I'll stop.
Go ahead, Javed.
Yeah. Mama, can you please stop sharing? Should we continue with this?
Okay.
Yeah,
Okay, sure.
you can open up your own
Sure.
slide.
Thanks. Is it visible to everyone?
Yes.
Yeah. Hi everyone. I am Javed Ali from Deep Kappa. I am also a research student at IIT Kharagpur, India. And here in Deep Kappa, I am a visiting AI researcher. I am working under a subdomain, PAT AI. Also, I was a ML engineer in one of the startups which we have done in oil industry. So let me talk about the two things which we are today dealing with. So one is innovation and one is invention. So invention is what we have done, what kind of R&D we have done, and innovation is what where we have applied all those R&D. And if there's some ambiguity, so we have checked and we have optimized those things and we have done the innovation from that invention. So first, let me show you what kind of invention we have done and what kind of research we have done. So this is actually a research area where I have worked and also made this kind of R&D to publish in very known conference, that is European Association of Geophysicists and Engineers. So the topic here was that, like, we have discussed about the automated boundary picking, that is kind of segmentation, which already Kamal has discussed with you. So on extending these kind of segmentation, but now we are using the unsupervised learning. Why? Because let's say we can have a situation where we don't have the label. So whenever we have the label, as you have seen in the previous slide, then we have a label for the facies. So we have detected the facies for the subsurfaces or under the earth. But if we don't have if we have a use case where we don't have the label, so how we will tackle that kind of problem? So that is one of the R&D which I am discussing here. Then we'll show what we have innovated out of both of these R&D using machine learning or supervised learning, as well as unsupervised or semi-supervised and self-supervised learning. So here I can show you, like, the talk outline will be what kind of area or what kind of data I have chosen, how the data look like, what kind of model architecture I have used, the data pre-processing, what were the steps was involved, the tricky step, then some conventional way to do that, to handle that situation, and how I have used the computer vision algorithm to overcome the conventional algorithm and to automate the things. That's how we have automated it. And then I'll show the results and the application, whatever we have. So far, let me explain you about this study area and the data. So the study area is from UTA. Is like open source data available from that area. So it's a forged data set, which is like have a 300 wells. Also, like it's seated around, like it's the depth of the area, the study area which we are doing is around 5 kilometers. So up to that depth we are doing the study. And in the data part, let me show you here. So in this data, what kind of data it is? What is actually happening here? So in the computer vision, we are dealing with kind of image processing. Okay, so similar thing is happening here, but in what kind of image? So the data is of oil industry, means the data from inside the earth. So there is the images which is from the inside the earth, and we are trying to make the prediction. We are trying to make the labeling out of that data. So here in right side you can see this is the data which we have get from the sensors. So we are just putting the sensor inside the earth by digging up boreholes. So we are putting the sensors and we are throwing the current out of those sensors and we are getting the potential. So if we have the current and potential, we can get the resistivity of particular area, particular depth. So using those resistivity values, we have plotted this kind of data that is in the form of image. You can see it here. So this is the image of resistivity value where the dark pixel is showing there's some kind of fault or some kind of edge is there, and the other light is showing the background. So means this dark will relate that there's kind of boundary, and that that is the thing which we are interested in to detect that. Let me talk about this model first. So in this model, we have input target input as a target image as an input, and the pixel level and feature representation are jointly optimized here. And these parameters are updated by gradient descent, which you are doing here. So in this proposed approach, the label prediction and network parameter learning are alternatively iterated to meet the following criteria. We are bounding this using three criteria. So the first thing should be that the pixel of similar features should be assigned to the same label. Means the if some same feature is there in the pixel, so that should be a same label. And the other thing which we are carrying off is the spatial continuity. Means the if something is near, so that should be assigned to the same label. Also, the third thing is that number of unique label, whatever the label we will get out of it, should be large, should not be small, so that like there can be a lot of labels. That's we are handling here. So I have used a 2D convolutional layer first. As the input I am giving a RGB image, then we are using a 2D convolutional layer. After that, the ReLU activation and then batch normalization. Same these kind of component has been repeated by n time. So this will act as a feature extraction. So from here we will get the feature extraction. After that, I'm using a 1D convolutional layer and then batch normalization to get the normalization map response map. After making it the high pass filter and the calculated the loss, and then make the clustering label. So this kind of label it have. So that's how I am doing it. And we have the three kind of losses which we are carrying off, so that everything has been considered. All these things, three things has been considered. First is feature similarity, means like if the pixel have the similarity feature should be assigned to the same level. That loss has been handled by this terminology. Then after there's a spatial continuity. If there's a spatial continuity, that should be a same label. So that is handling by this a lot. And also like there's a weightage factor mu, which is for the tuning. And also in the last, we are using some scribble information that I will share in the later part. So for that loss, we are considering the third part. Now coming to the data processing. So here we have a lot of use cases. So first of all, we have this image where this is the raw data, and here you can see the white strip that has an NaN value. If we have in a data, let's say you have seen in the computer vision problem, like we have a lot of missing data, we have a lot of NaN value. So how it look like in the real life? So that is how it look like. We have a white strip, but this is not usable. So this is making our data more error type. So that we are trying to reduce this error, or we are trying to reduce this NaN value, or trying to fill this NaN value so that we can get the continuous pixels. That is I am doing here. So that's kind of data processing we have done. and after that we are trying to see it in a grayscale,
Mm.
so that like the view can be clear, so that like the only edge which we want to detect is in white and the other thing is in black. That is the background. Next thing what we have done here is an image thresholding. Image thresholding we have done because we want to clarify, we want to know like what kind of label, what is the label and what is the other background. So just to make it into two classes, we have user thresholding. We have fixed the value where above that value there will be one pixel value, so that will be denote to this edge, and the other will be act as an background, so that is black here. Third thing here, this is very important, that is edge detection. So you have seen in a lot of computer vision things that we have some algorithm, physical algorithm, like people are using to detect the edges of any image. So that is also we are implementing here in seismic in the oil data, and we are detecting this edge using that canny edge detection and hug transformation. What the canny edge detection do is used to detect the edges, and what hug transformation used to do, it it detects the lines. So continuously for the edge detection we do the canny edge detection and hug transformation, so that we can get the whole clear sinusoidal kind of wave here which we
Mm.
are getting here. Okay, now come to next slide. So here are the results. You can see these are the two instances of the result. Let's consider the slower one, where you can see in the data we have this kind of pixel, dark pixel, which is showing the boundary, and this is the whole data. So in this sinusoid is showing the boundary. So in the first image, like we have reduced the NN value and all, and whatever we have found from Kenny S detection and hug transformation, that is acting as a scribble or kind of pre-information which we are feeding to our network, so that our network can easily cluster the data. So it will help for our network to get the data. So that Kenny S detection, from the Kenny S detection we are getting this scribble, and now we are running our algorithm and we are able to detect, automatically able to detect this kind of, like, this is black, this black one is the bounty, and other thing is the, like the data, the like kind of the data which is we are not interested in. So we are able to label it, like we are able to get in two labels, where is the boundary and the other one what the apart from the boundary. So these were the results I got. After that, we also have developed a React application, React based application, which we can use in the real life. We are using in the real life. That is also like we have discussed in the last lecture, in the last webinar. So like we have shown you. So similar, this is the kind of similar algorithm app which is using the this right now use case which I have done. So in this as in first tab you can see there's a tab where we are putting the input data, and the second we can do this kind of processing, hug transformation, carrier detection, and the in third, like we can do this kind of feature analysis using this log. So all these we have done in this React Beds app. After that, let me show share you something which is the innovation. So whatever we have done till now was the invention. What kind of R&D we have done? So we have done two kind of the R&D. We have some label data. This is the Kamal and the team has done. So they have done kind of segmentation, and and me and my team has done on unsupervised learning. That was the data which don't have the label. So these two type of work we have completed. After that, we found like this is the R&D. Can we do some kind of use case, or can we find out something which can provide the profit to the real world or to the real industry, that is a huge oil industry. So can we do something? So for that we did a kind of innovation, which is a startup, which is we have a friend who is also leading that startup, and that is based in US. So let me share what kind of startup it is. So here is the insight of that. We are doing kind of a startup where we are tackling a real time problem, which is right now in the oil industry. So in oil industry, what we have this kind of data, which is very unstructured, raw PDFs, and in raw PDF we have a lot of data, but we don't have a digitized values of these data. So what we are doing here, we are trying to get the digitized value out of these raw data, these PDF. So we have used some algorithm, which is like NLP algorithm and machine learning algorithm. Also, like we have used CV tools, which is like OCR and CVET tools, which used to do the annotation. So what we are doing here, this is the input, the raw PDF, and in output we will get the digitized value of it. and we are getting the digitized value of particular log. Like there's a lot of traces you can see. So whatever traces you want to get, you want in the digitization output, you can get it. So that's how we are doing kind of this processing. And in pre-processing, I can tell you what we have done. This is a raw data, and so we have taken the step, like we have cropped the data only for one uh, track, and then we try to digitize it using CVET tool. That is like a computer vision annotation tool, which is like open source tool which we have used, and then we have completed it and then do the digitization. So we are getting the data in the form of a digitized value in images value, or we are getting this output in the form of .csv file, so that at each data point, each depth point, we can get the data, whatever data is present in this kind of curve. So this is the application which we have used here in Seismic in oil industry. But there's a lot of things, lot of files, lot of PDF data is available in lot of different domains. So that kind of processing we can also do in different domains. Let's say in image processing, in some other industry where the main data is in PDF format, or in like text file. So like in that way we can convert it, or we can digitize the data, we can get the data in numerical values, in numerical values in CSV format, and then using those data we can do whatever kind of analysis we want to do, and whatever kind of like the numerical processing exists, so that like we can use those data. Right now if it is in PDF, so only the people who has the access of the PDF can use it. But once the data is in digitized form, we can share it in different way, like through the email, through like other platform, social platform, or any sharing platform, so that we can use, anyone can use. And this is the power of like a kind of open source. When we have a digitized data, so we can open source it. And right now the world is testing that data. Right now we are able to do the lot of machine learning, lot of deep learning. And how we are doing this, because we have the kind of open source data, iris data, some images of like medical, you have chest x-ray kind of data, so you can detect what kind of like do the person have the pneumonia or something. And so like digitization is like kind of a very innovative thing which is needed right now in the industry. So we have done the use cases in Seismic in oil industry. But anyone, if any you have any kind of idea, if you have any kind this kind of data, so you can use in the real time, and like you can make your own innovation, you can start your own startup. And like we can also like provide the methodology, what kind of methodology we have used, if someone needs this kind of discussion in future. So that's what I think Samar will continue on the approach how we have done this. So that will be good.
Go ahead, Kwame.
Stop sharing.
Or you can continue sharing this, and Kwame can just talk. That's also possible. Up to you.
Can you guys see my screen?
Not yet. Any questions you guys have? I'll just look into the chat. It is indeed, it's a very impressive presentation going on so far. I see Fred commenting. If you have questions, do please keep asking. I think the key thing which Javed just mentioned is, and I think Tanishta mentioned as well in the first talk, is a lot of people think boring industries, which people have been labeling some industries versus exciting industries, and is that the learning comes from a totally different domain. A healthcare domain data is being used to understand subsurface seismic data. And those are very, very interesting sort of domain understanding that we are transferring to different domains. And that's why it's super important for you to realize that sometimes you can be a superstar in a boring domain because you understood the correlation between a totally different industry, healthcare, or even understanding maybe sort of astrophysics or something else, or other simpler sort of information which has similar modality in when you look at the data. And this is where I think boring sort of industries become very exciting to work in. And I really want to emphasize that, because I'll share something later once Kwame is done, with how we are actually moving forward with Black Oro Partners, the startup in US, to go into carbon capture, carbon sequestering. I'll show you one slide, actually. It's a project we're calling Project Inertia. But go ahead, Kwame.
Yeah, okay. So the way our approach worked is basically we try to mimic how we as a human try to read this graph. We first try to read this line, characteristic line, and then we capture this information, and then we translate this information to this graph, and we try to figure out that which particular graph belongs to which particular which particular logs. Logs could be resistivity, gamma ray, porosity, permeability. There could be n number of logs. So we have to figure out, we have to first look into this this is basically called header, and this is what we call the graph. So we have to translate the header information to the graph, to this particular graph, and then try to uh, get the actual values based on the scale given over here. So all these things are actually captured in our model, that in our model. So we have actually used the modified unit, which we actually showed in the very beginning. uh, this We have used actually this particular model in our invention, which we were developing in our invention stage, to and translated it to innovation stage, and we used that network with four residual transpose reducible blocks. And we have used Adam optimizer. It's basically a hybrid optimizer which tries to optimize the model weights and parameters. And we have used several, I mean, all these are actually technical terms, which are this binary cross entropy basically tries to figure out that how accurate, how confident your model is in predicting that whether in predicting these signals. Basically this is the signal, and this binary cross entropy will tell that how confident your model is in predicting the right signal. And so we have used this binary cross entropy as a loss which will be used to optimize our model weights. Similarly, this mean intersection over union is what we have used as a metric to judge how good our model is. Once we have trained our model for 100 epochs, which ran about 4 hours on a DGX box server, then this mean intersection over union is a technical term. It basically tries to say that how good the results which you have achieved is. It's a typical computer vision metrics. So once we have this mask from the model, there is a step called post processing. As you can see that there are some, this is the basically the signal which we want. But along with that, there are few unwanted signals that came along with it. So we have to remove this in the post processing steps. So after removing this, we have used some morphological methodology, where we have to remove all those small dots from the mask. So once we have that, we have a cleaner version of the mask. And from the cleaner version of mask, the way we are trying to convert this mask into a CSV file is that we will be looking into each row and try to find out the index for each white pixels, and then based on the white pixels and the header information which we have captured from here, we will try to convert this CSV this mask into an actual log values.
Hmm.
So these are a few snaps from the app that we have developed. So in the first panel we will upload this scan file. We will be able to zoom in, and the user will be able to look into scroll down all the way, so that he gets satisfied that he has uploaded the right file, and there is no manipulation into the file. Once we have done that, then we will hit this button, and then at the back end it will try to run our model, and then it will give the mask, and finally this panel will give us the post processing step. So as you can see that the scanned image goes in, and we get this mask from we get the mask, and then after post processing we get the final post process mask. And after that we can user can easily download the CSV file. So similarly, this is another tab which actually, once we have digitized the logs, then it will take those CSV file and do a correlation study In the earlier week, we have showed this video. We have showed the demo of this video. So if you guys are interested, you can look back into the previous talk recording. So yeah, that's it. Terry, if you can take ahead from here.
Yeah, great. I was just typing. I'll just spend the last like 2 minutes, not more. I just shared a link on one of the webinars I did a few weeks ago. And it's all about understanding how do you actually organize a team that can succeed in a way that you actually take inventions and create roles within your organization to become a company. I mean, you don't, startups obviously also have that same sort of challenge, but existing companies as well. I mean, if it's Texas Instrument, which is one of the big companies out there, or if it's a mid-sized company with a few hundred to a few thousand employees, they face similar challenges. And so basically, I just shared a link in chat. Just take a look at it. You can run it. And this is a workshop I gave a couple of weeks ago, or to talk about how do you organize roles. So this, you just spoke to actually two very bright people from this department, which I call my AI department. And both Kwame and Javed, but there are a bunch of other researchers who do a lot of interesting things with many different areas: ethics, healthcare, in text analytics, or inside totally different sort of industries. Climate change is another sort of startup we are launching. So this, you spoke to the AI guys. In the last week or a few days ago, we spoke about the MLOps and DevOps people. And then you have the IT people. So this is essentially the IT department inside a big company. I've worked there. I used to be a manager of IT department when I used to work at university. This was a long time ago. And I used to also manage all the workloads, etc. So all these people within our company, within our startup, are different individuals with different skill sets. And eventually, you have to tie all these things together by bringing these experiences and expertise together in order to actually create something that is back-to-back, end-to-end, done in a manner that the researchers who are in this department understand what they have to give in package form to this department, which is, let's say, the developers or the deployment people inside the IT. And then you have the typical administrators inside the IT department who are monitoring and doing all kinds of things. So in a way, this is what you need to be doing in order to actually understanding that if I am a researcher, I need to understand engineering is a very, very important part of my capability. I cannot just be a random researcher working in an R&D department without understanding that the invention that I'm making needs to hit the road. The same applies to the engineers as well, who need to understand what is being invented and can I interpret and understand all these complex techniques these people are using. This level of understanding when people have, then you have a very successful organization. So moving forward to the next, so once you have this MLOps life cycle, you can actually then move into starting to actually going and capturing domains. So carbon capture or carbon sequestration, carbon capture utilization is a big and a massive domain that is emerging, and ESG, all the other sort of, environment, the climate change today, whether you believe it or not, is upon us. And now we are doing the same things. We have initiated an internal project we call Project Inertia, that is going to be focusing on carbon capture. So essentially, it's all about carbon solubility of the ionic liquid, or IL. And you need to be the company, or any individual or a group of company that is building the most effective and efficient model that can actually capture carbon from a point source. So here you have factories that have a sort of emission of 4 to 20%, and from the cities you have, from the atmosphere, you already have 400 parts per million. That's a term you use for to understand how much parts of let's say the carbon CO2 are in the atmosphere, or it could also be in seawater or any other sort of region, or on rocks, for instance. And these emissions, actually, you have to understand these either at the molecular level, or you can, so basically you need to understand the process at the molecular or at the process level scale. So this, if you understand this and you know what to do with it, you actually make your life a lot easier to start sort of capturing carbon from sea level, from rocks, from even thin air. There's a lot of other techniques, and essentially start actually creating various pipelines. And this is how you become a successful sort of expert in this area. So you have a pipeline 1 doing 1 operation, pipeline 2 doing 2 operation, and so on and so forth. So this is how we try to understand a new domain. I'm not saying I'm a carbon capture expert, but once I know that I have ML ops as something I can research, which is this area, I can enable and deploy this, which is this part, and monitor the performance of the models, which is this part. Then it takes me very limited amount of effort to understand that, okay, so what do I need to do in order to understand what are the thermodynamic properties, for example? I mean, all these is simple chemistry, right? So you have to understand the adsorption, absorption, not adsorption. Adsorption is also technique, but absorption-based carbon capture, the better and efficient way you can capture and predict those optimization processes, the faster you will reach a success rate of being a great carbon capture sort of company or a project. So this is one of the few things we are doing, and the similar approach we apply to very different techniques. So you can see here, you can go into healthcare, you can do the similar thing, and we have done an award-winning project with the European Union, and as you can see here, so this was a European Union project on breast cancer, and this is a project on dental. So similar approaches you can apply once you understand this part. So, and the key to success of doing these things is essentially basically taking your, let me just stop and kind of finalize. This is the last presentation, so let me put the camera on. Oh. Okay. Oh yeah, there you go. So So the key is to make sure that the interdisciplinary capabilities of your team, so there's a research group of people, and you have engineering, and you have software development. Once you're able to bring a team of 6, 7 people, maybe even a smaller team who have these interdisciplinary capabilities, it's pretty much possible for you to actually set up a very successful project that can be commercial. So today we have Fred here. And perhaps maybe Fred, it might be interesting for you to do the final kind of closing of this 3-part webinar series we did with UTD Dallas. I know you'll have a lot of questions. We'll try to answer most of these questions to you guys as well. Fred, maybe sort of giving you the final word, and then we can sort of close this conversation, because it's been, to me, it's been a wonderful sort of revelation myself personally. As I saw us present at UTD Dallas, it was a last-minute sort of conversation I was having with Professor Jay, and I'm super excited that it kind of turned into a very interesting knowledge-sharing conversation, which I hope to the rest of the UTD community has been useful. Obviously, it's not the first. We'll be coming back, and we'll be teaching you these techniques as well at UTD Dallas, hopefully in other universities also in Texas region. But for now, maybe Fred, what do you think? What's your takeaway from all these 3 webinars? If you were not involved in this right now, you're leading this, you're in the middle of this project. But if you were a professional, or maybe an oil and gas, or maybe a new energy sort of executive, what would be sort of your key takeaway?
So I think first of all, great presentation from Javed and from Kamar. Some of the stuff that they came up with was totally amazing. I think and I appreciate the University of Texas Dallas for helping us out and present some of our findings, and hopefully that inspires researchers and young engineers to cross collaborate and be able to join a team or create a team and expand their knowledge of what is actually possible. From a startup point of view, I think the most important part is, like, if you have an idea, and this is where I see where a lot of startups they falter. They're like, well, maybe it seems easy. I can do that on my my screen. On my desktop, or I can create this cool app on my own. But if you really want to be a startup and you really want to take it to the next level, then I would suggest that you find experts that have an integrated team, from the research, from the capabilities, from the people that understand the hardware and the software, and then also be able to deploy those products. So once you have a good idea, and sometimes I've seen people that have not such a great idea, but if they have this basic understanding of how to integrate all of those, domain expertise, from the research, from the engineering, and from the commercialization project, then you can launch and have a very successful product, and then you can scale up even faster. So I think that from what the education that live AI is providing, that real AI is providing, the Deep Kappa team obviously has an amazing group of individuals, very talented individuals that can put all of these things together, and you can learn from what they're doing. Then you can keep that in the back of your mind, so that way you can take a product from in my case, from a dream, something that could be a tool not just for yourself but for other people. Then you can really learn a lot and scale up. And if you start off with these basic understanding of, hey, I know what the research team is doing, I know how that is going to be implemented into the engineering and the design, and then start off with something simple but with all those different components, and then integrate those components, and you can quickly scale up. So keep that in the back of your mind as you proceed through any of your adventures, any of your startup ideas. How to ask yourself the basic question: if this is a great idea, or if this is a so-so idea, how can I quickly integrate it and then scale it up? And then I think that anything is possible. And you never know where your idea is going until you actually apply it, test it, and then have people use it. So I think with those kind of questions, Terry, or that kind of thought process is where I think we are right now. And I think that all of these ideas can quickly be scaled up once you design and integrate your workflow in that manner.
I think this is sage advice, Fred. Thank you for that, and obviously thanks to my great team, wonderful team. But most importantly, thank you all for sitting and listening, and also all the way from Thailand. You're spending your night sitting and listening. Inspiration comes in different forms. We learn a lot on a daily basis. Each time I come and teach in Dallas, I learn a lot more when I go home. So, I mean, to me, it's just a hack. The reason why I come to teach is secretly I'm a student of I just want to learn together with you guys. And we've recruited so many bright people from UTD Dallas, also into Deep Kappa. They've done wonderful internships. Some of them have stayed for a longer period. And some guys have been inspired so much that they've started pursuing their PhD ambitions. I'll be definitely back myself very soon. Me and Professor Jay will figure out some way to be there. And these are longer sort of workshops, hackathons, and boot camps where I spend literally a full week with you in that big hall, the big new beautiful building out there. And spend time teaching you all the fundamentals of machine learning and deep learning, give you all kinds of projects, including this project will also kind of create something. So stay in touch, please. Reach out to Fred. He's close to you. Me and Fred will be dropping by as well, hopefully also physically, to try to enable sort of a workshop that'll be helping us also to recruit folks, because we are sort of building out this startup and we want to get more people on board. So obviously this is also very serious and very directly and openly transparent, just to be very transparent with you guys. A hiring sort of also exercise for me, for Fred. So do please reach out to us if you have any questions. Reach out to Professor Jay if you don't have my email address, and he's going to put you in touch with me. You have any questions? I'm very happy to take any questions if you guys have. I'm willing to spend another few seconds listening to you guys. Any burning questions someone has? Anyone? You can raise your hand or or just, you know, open up your mic and just ask. Don't be shy. And most of the times we're kind of shy because we think, oh, I'll look stupid. But I think don't worry about it. All right. I guess if you do reach out to me on email or through Professor Jay, we thank you and hope and we'll try to rerun this also and provide recordings so more students and professionals can watch it. I thank you all. I'm wishing you a wonderful weekend and a safer weekend. I'm very happy and glad to hear that most of the students at UT Dallas have been able to come to physical locations, which is fascinating. So thank you. Take care. Have a safe weekend and stay safe. See you guys. Bye-bye.